Hey guys, this is Mrs. Tran-Bloom. I am trying out a new recording method today. Hopefully it works well, okay? So we are recording 4.3. The title of this is called Complex Zeros, Fundamental Theorem of Algebra. So Fundamental Theorem of Algebra, it's a skill that's really important. So we have a few vocabs and a couple of theorems, okay? The first vocab is called the imaginary unit, and the imaginary unit is used in algebra. Let me get my pen. In algebra 1, it is denoted as I. Okay, sorry. This is my first time recording this and I'm having a hard time. So I is equal to, okay, so I, ooh, that is some ugly equation, square root of -1, okay. I'm kind of getting used to this. I'm using a stylus and I've never used it before, so my writing is going to be funky for a little while. So imaginary unit is I equal to square root of -1. Now we can also have I square and I to the third, okay? I square, actually let's start with I square. I square, let's erase that really quickly. So I square is going to be, if I were to square both sides, okay, take this and square both sides, and I square is going to be a -1. And we can also have I to the third and I to the fourth and so on. Complex number, we're going to do a standard form. So in standard form, is A plus BI, where A and B are real numbers. Okay, so I'm going to give you some examples. So i.e., it's an example. This could be a complex number, 5 plus 2i, that's a complex number, or -10 minus, let's say 11i, okay? Or I can even do square root of 2 plus pi i. All of those are complex number. How about this? This is going to be interesting. 0 plus 3i, okay? 0 plus 3i is identical to, by the way, 3i equals to 3i, okay? And that's a complex number. How about one more, okay? How about if I were to do radical 5 plus 0i, which is simply just radical 5, isn't it? If that's the case, then a real solution, which is just radical 5, it's also a complex number. So complex number is a bigger set of numbers, okay? A bigger set of numbers that also include real numbers as well. So complex number is solving for all solutions, real and imaginary. This leads me to bring up this theorem, fundamental theorem of algebra. A variable in the complex number, let me just get a highlighter right quick, okay? A variable in the complex number system is referred to as a complex variable. A complex polynomial function f of a degree n is a function of the form, and we've seen this form before. F of x equals a sub n times x to the nth plus a sub n minus 1 times x to the nth minus 1 plus so on and so far a sub 1 times x plus a sub 0, where a sub n minus 1, a sub 1, and a sub 0 are all complex number. Keep in mind, complex numbers is also imaginary, okay, and real. So just don't think of it as only imaginary. Where a sub n equals cannot be 0. If it's 0, then this whole thing is gone. N, which is the exponent, it's a non-negative integer, aka positive integer, and x is a complex variable. Now, x is called a complex variable just simply, here, notice this right here. X is called a complex variable because we're going to be solving for complex 0. That's the only reason why it's now called a complex variable. So as before, a sub n is called the leading coefficient, which is in the very front of f. A complex number r is called a complex zero if, when I plug r back into f, my remainder is 0. Okay, so this is restating the polynomial, now called a complex polynomial. But all of it is exactly still very similar to the regular polynomial. Every complex polynomial function f of x of a degree 1 or bigger has at least one complex zero. What this means is I will always have a solution. Will always have a solution. Okay, so in a complex solution, when it says solve under complex numbers, you can never say no solution or no complex solution. You always have at least one. These two are related, okay? Every complex polynomial function f of x of a degree 1 or bigger can be factored into n linear factors. Not necessarily distinct, that means they don't have to be different, of the form. First, you take out the leading coefficient, okay? Because all of this has to be linear, that means the power, this power right here must be 1, okay? Power of 1. And they can all be exactly the same. Just because the word is linear, that means I can't have anything but a power of 1. Where a sub n, r1, r2, rn, these are the roots, are complex numbers. That is, every complex polynomial function of a degree 1 or bigger has exactly, and this is so important, has exactly n complex 0. Okay? So what this means is if degree is 5, then we have exactly 5 complex. Ooh. Sorry, that doesn't look like the word complex. 5 complex roots or zeros, okay? Roots is used for 0 as well. So we will always have at least one solution, and these are related, okay? If n is 5, then I have exactly 5 roots. If n is 4, then I have exactly 4 roots, and so on, okay? Conjugate pairs theorem, another very important theorem, okay? Let f of x be a polynomial whose coefficients are real numbers. If the first root, which is a real number or complex number, real is also including complex, if r equals a plus bi is a 0 of f, then the complex conjugate, r with the bar on the top, it's just denoting that these two are conjugate of each other. The conjugate is a minus bi. It's also a 0 of f, okay? So whenever you are having an imaginary answer, then there has to be a conjugate of that imaginary answer as well, okay? And this theorem is super important. Let's use these theorem for this problem, okay? Example 1, find the remaining zeros of f. You have a degree of 6. That means there should be 6 complex zeros, okay? Currently, they give you 1, 2, and 3. They give you 3 roots. Oh, can you change that to an I? So they give you first root is I, second root is 3 minus 2i, third root is negative 2 plus I. If you have a degree of 6, you know there has to be exactly 6 complex zeros. That means they give you 3 means that we have to find the remaining complex zeros. That means there are 3 more, okay? The conjugate pairs theorem says, hey, if there is an I, then there has to be a negative I. If there is a 3 plus I, that means there is a 3, there's 3 minus I, there has to be a 3 plus 2i. 3 minus 2i. Then the conjugate is 3 plus 2i. If there is a negative 2 plus I as one of the complex roots, then the conjugate, you don't change the front, by the way. Okay, the front maintains negative 2. You only change the sign in the middle. So the conjugate is negative 2 minus I. So these right here, box this up, it's my remaining complex zeros. If I count them up, I should have a total of 6 because the degree of 6. 1, 2, 3, 4, 5, 6. Okay, because of your degree 6. Now, there's also a typo in here. Can you fix this right here? This should say 2 minus I, comma, I. Okay, so do me a favor. I would like for you to try this on your own. On your own, okay? And I'm going to work this one out with you because this one's slightly different. So next year, I'm probably going to change B to a check for you, and then check for you is B. So let's do check for understanding together. You have a degree of 5, meaning that you should have 5 complex roots or zeros. They give you 1, 2, 3, and 4. That means you have one remaining complex 0. There should be 1, okay? Well, 0 is a real number. 1 is a real number. 2 is a real number. These real numbers do not have conjugate pairs, okay? Only the imaginary one. So there's one imaginary answer, which is I. So its conjugate pair is negative I. So for this problem, you only have one remaining complex root. Okay. So now that you are working this on your own, when I see you next time in class and I stamp this, make sure this is completed. And as you are completing this, let me give you a joke of today. What do a baker and a millionaire have in common? What do a baker and a millionaire have in common? They are both rolling in dough. They're both rolling in dough. Get it? Baker, he or she needs flour, dough to bake. And millionaire, they have a lot of money. Okay? All right, this is the end of the note. I will see you in class.